Welcome to lesson 2.6 on rational functions and asymptotes. So in this lesson we'll learn how to determine the domains and find asymptotes of rational functions. So first of all, let's talk about what is a rational function. That's any function where we have some kind of a function in the numerator and we have some kind of a function in the denominator. So the parent function of the rational function is simply 1 over x. And we'll explore this at much greater length in just a few minutes. Now, a vertical asymptote, that is something that's going to occur in the graph of a rational function. And if you think about our parent function, 1 over x, the domain of that parent function is just naturally x can never equal 0, right? Because we never want to divide by 0. So if x can never equal 0, the asymptote is what occurs as things get very, very close to 0. So if we look at the parent function of 1 over x, it looks like this. And then we have another similar curve on in the third quadrant. So as x gets really, really big, so I'll say as x approaches infinity, okay, so that's as x goes this way on the graph towards the right, then 1 divided by those numbers gets really, really, really teeny tiny. So say x is 1, if x is 1, that's right here, then when we plug that in we get a 1. And so that's that point on the graph. But as we go, say x is 10, then we have 1/10. So our point gets really, really small. As we go to 100, 1/100th, 1/1000th. It's just as x approaches infinity, f of x approaches 0. But even when x is 1,000,000, 1/1,000,000th is still not 0. You're going to get very, very close to 0, but you're never going to actually get there. Then let's look at this section between 1 and 0. As x approaches 0, because, see, it can never actually equal 0. Say x is 1/2. Alright, so I would plug in 1 over 1/2, and then 1 over 1/2 is equal to 2. So see, at x equals 1/2, we start getting bigger. As x equals 1/100th, then x equals 100. As x equals 1/1,000,000th, x equals 1,000,000. So you can see how it goes. The function value, as x gets very close to 0, the function value it just keeps going up. The smaller you make x, the bigger the function is. And so that's the type of behavior that happens at an asymptote, where you can approach a number, but you can never quite get there. So the definition of a vertical asymptote, the line x equals a is a vertical asymptote when as f of x approaches infinity, or f of x approaches negative infinity, then you approach that asymptote. So I feel like, are we going to define it later? No. Alright, I'm just going to write that all out. So x equals a is a vertical asymptote when as f of x approaches infinity or f of x approaches negative infinity, then x approaches a, and I'll say, so either from the right or from the left. And so this is an example of what a vertical asymptote looks like. That's the line It's the y-axis, but it's also the line x equals 0. So now we also have a horizontal asymptote in this graph. And it's the same thing. Y equals b is a horizontal asymptote. And I'll just abbreviate that, HA, of f when as f of x approaches b, then you get these x values that are approaching infinity or negative infinity. So it's that infinite behavior that's going to be an indicator of whether or not you have an asymptote. So we have studied in Chapter 1 domains, and this section is all about how the domain of a rational function of x includes all real numbers except x values that make the denominator 0. So, the process that you use for finding the domain of a rational function of x to find the domain of a rational function of x, you factor and simplify to find potential zeros in the denominator. And we may or may not add to that definition as we go forward. So in example 1, we want to find the domain of this function, 1 over x squared minus 9. So the key is you want to be able to factor that polynomial. So that's clearly a difference of squares. And then you could take a look at that factored form and say, all right, what values of x must be excluded from my domain because they would give me a 0 in the denominator. So there's several ways we could write our domain. We could say x is all reals except that x cannot be equal to 3 or negative 3. So that would be one way to write our domain. Another way would be to use interval notation. So we could go from negative infinity to negative 3, but it can't be equal to negative 3. We can go from negative 3 to positive 3, but it can't be equal to positive 3. And then we could go from positive 3 to infinity. So that would be another good way to write our domain. So another way that you can use to find your domain is by graphing or visualizing the graph and seeing if there are any asymptotes. If there is an asymptote, that means that that value is excluded from the domain. So let's look at how we write some of this asymptotic notation. We say f of x approaches 5 as x approaches infinity. So that means as x gets greater and greater and greater, then my function is going to get closer and closer to 5. So it also means there's a horizontal asymptote. At y equals 5. So let's take a look. Here is some function notation gobbledygook, but basically we're saying we've got our numerator over our denominator, and here's our numerator function. And so these notations mean the coefficient of the nth term and x is to the nth power. This is giving you an indication of how many terms are in your function. And then we have the coefficients of the terms in the denominator. So where there's no common factors here, because if something could divide out, we would of course divide that out before we get started saying where the asymptotes are. So the graph of f has vertical asymptotes at the zeros of the denominator. So the vertical asymptotes are easy. If it can't be equal to that number, that's going to be where your verticals are. So the graph of f has at most one horizontal asymptote determined by, and that's the degrees of the numerator and the denominator. So n is our numerator degree, m is our denominator degree. So if n is less than m, then y equals 0 is a horizontal asymptote. So let's look at what that means. So n is the degree of your top polynomial. So if you have, say, x squared plus 2x plus 1 up top, then m is the degree on the bottom, and we're saying if n is less than m. So here we would have x cubed. Okay, so if you just look at these guys and reduce, you end up with 1 over x. X squared over x cubed is 1 over x, and that's kind of the parent function that you're thinking about. Then you end up with y equals 0 as a horizontal asymptote. If n is equal to m, then whatever your leading coefficients are, a and b, whatever that division problem is, then that is your horizontal asymptote. So in this example, I would say if I had 2x squared plus something 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 over x squared minus 9, say, then that 2 over 1, that line would be where my asymptote is located. If n is greater than m, so that would be like 3x cubed over 7x squared. So if we just look at the 3 and the 2, the degrees, x cubed divided by x squared is x. That's a line, and we don't end up with any asymptotes with that. So if the top degree is bigger than the bottom degree, then we end up with no horizontal asymptotes. So let's take a look at example 2, find the asymptotes of the function. Okay, so we've got a couple of different things going on here. We have the degree of the function and we have the coefficients. So up top we have a degree of 1, and on the bottom we have a degree of x squared. So we would look at which one of these 3 scenarios does that match with. Well, we have a smaller one on the top, a bigger one on the bottom, so that is scenario A. So then y equals 0 is a horizontal asymptote. So I'd like to show you that rather than just telling it to you and hoping that you'll believe it. So let's go ahead and enter in this function. I'm going to put 2x minus 1 in parentheses divided by, and then my second function I'm going to put in parentheses, x squared minus x minus 6. And so I'm going to hit graph, and then I'm going to zoom. Okay, so we also have some vertical asymptotes. So this right here is a vertical asymptote, and your calculator doesn't know how to deal with that. It actually connects the dots, which is not correct. But what we're looking for right now is that this y equals 0 is the horizontal asymptote. So you can see that your graph never actually touches that y-axis. So let me go ahead and change my window a little bit. And then let's explore those vertical asymptotes now. I can kind of see there's one over here on this side and one over here on this side. So what I neglected to do, we figured out the horizontal asymptotes, but we didn't look at what the vertical asymptotes would be. And to do that, we have to factor our denominator. So let's go ahead, and if we're looking for two things that multiply to be -6 and add to equal -1. So 2 times 3 is 6, and they're 1 apart. So if I want it to equal -1, that's going to be -3. So when I rewrite this thing in factored form, x plus 2, x minus 3, so I have vertical asymptotes at x equals -2, x equals +3. Okay, so my last question is to give an example of a real-life situation where you have asymptotic behavior. And so I am going to leave that for class time. You can read the example on page 146 about cleaning coal, and cleaning pollutants from the air. And basically you can spend so let's just talk about it in general terms. You can spend no money or very little money and have tons of pollution in the air. And the more, so I'm going to say on my X scale is money, and then on my Y scale is pollutants. So you spend very little money and you end up with tons of pollutants. And as you spend more and more money, you're going to be able to clean more and more pollutants. But there comes a point, and this is in business, they call this the law of diminishing returns, where you could spend $1 million and you could be down at 0.1% pollutants, and then you could spend $10 million and you might be at 0.09%. So it's like, is that extra $9 million you just spent worth it to get rid of 0.01%? Like, yes, all this money you spent, it was worth it. And then there gets to be a point where you're never going to remove 100% of the pollutants. It's got an asymptote at 0, and you could spend billions and billions of dollars and still never get it all. So you have to decide, kind of in business and in real life, a cutoff point. How much can you spend, and how much of whatever it is can you stand? So we'll talk about that more in class. And this is one of those concepts where generally in my tutoring business, this is where I started to get lots of tutoring clients, because this is something that's going to require you to study and to look at the charts in the book and to practice quite a bit in order to understand it. So we'll go over it in class some more, and then you can do your homework problems. Thanks for watching.